You hear the ping. Okay, go ahead.
Okay, here we are gonna present the challenge 6, learning to rank with pre-ensemble for NLP. But there's a group member who is gonna who is gonna present the treat part, but he's not here, so maybe we're gonna skip his part. And this is our overview, and I split this task or challenge into maybe 4 parts. The first part is mine. I split a data set because the data set is kind of messy. I process it so my teammate could use the data set more easily. And the second part is feature engineering. And the third part is a random forest baseline. And the fourth part is learning to rank. Yeah. And first is introduction. Before I explain what I built, I will first introduce the intake dataset. Intake dataset is a question answer ranking dataset representing a community QA scenario. In this dataset, each query is a question, and each document corresponds to a candidate answer. And our task is for each question, rank the candidate answer by relevance or quality so that the best answers appear at the top. Therefore, the dataset consists of 3 main parts: the answering corpus, the set of questions, and the human relevance judgment, which are provided as queries. And intake provides graded relevance label from 1 to 4. However, this assignment uses both binary and graded views. For example, MAP and MRR typically use a binary relevance, while the NDCG at 10 and the LambdaMART requires graded relevance. So in my processing, I would say pre-processing, I standardize 2 label formats. The first is the binary label. Relevance 3 or 4 is treated as relevant, and 1 or 2 is non-relevant. And the second is a graded label. I convert the label 1 to 4 into 0 to 3 by subtracting 1. And this prevents inconsistent label conversion across teammates and ensures that all model and the metrics are directly comparable. And next is the data splitting strategy. I prepare several splits that are commonly used in this challenge. And the first is we have the basic train and test split. And second, we have the split 200 train and the split 200 valid, which reserve a fixed set of validation queries from the training set for hyperparameter tuning and model selection. And you're making the experiment reproducible. And finally, we have the test non-offensive, which remove the offensive or noisy question and is typically more suitable for reporting the main test result. So I package it all these split in the same standardized format so that everyone could simply load the file and start working.
Very good.
Yeah. And this slide summarizes the core goal for my part is converting the raw data set into a model-ready standardized interface. The pipeline is you load the queries, documents, and the queries. Then for each query entry, join the corresponding query text and the document text to form a QID and document ID pairs table. And next is I generate two standardized label format, is binary and graded. Then I build a query grouping information required by learning to rank model, which is the group size. And finally, I export the process output into a fixed file format, so that my teammates can directly perform feature extraction or modeling, training, and maybe evaluation.
Mhm.
Yeah. And this slide shows a key dataset characteristic, the distribution of the number of the candidate answer per query. For the train split and the test non-offensive split. And on the left, the train distribution is highly skewed and has a clear long tail. The most caution have relatively few candidate answering, or maybe candidate answers. But a small number of queries have a very large number of candidates. And on the right is the test / non-offensive split. It's more concentrated, and most queries have candidates and counts roughly in a range about 20 to 45, which is more stable. Yeah. And this leads to 3 practical implications. First, the evaluation must be done at the query level. Otherwise, the long tail query can disproportionately affect the result. And the second is that learning to rank requires correct query grouping. So keeping row order aligned with the group size is very crucial and is critical. And the third is in feature engineering, especially BERT embedding, query with many candidates require carefully efficient and catching strategy. Yeah.
Caching.
And this
Yeah,
part is for
so
Rod.
I'm going to talk about my part, which is feature engineering. So I'll explain it with this picture. So we start with the raw data, which consists of like query, document, text pairs. So however, this data is purely textual, so it cannot be directly used by machine learning models. So what I do is to transform raw text into meaningful numerical features. Next slides. So first I'm going to talk about BERT, which is a pre-trained language model that learns contextual representations of text. So BERT understands a word based on the surroundings context. And this figure illustrates how BERT represents text as numerical vectors. So you can see that at the top, you can see the input tokens. And BERT first tokenizes the input text and adds special tokens such as CLS and SEP. And the CLS token is a special token that represents the entire sentence. So each token is then mapped to a token embedding, which represents the meaning of the word itself. Then segment embedding indicates which part of the input the token belongs to, like for example, sentence A or sentence B. So this allows BERT to distinguish between different text segments. Then positions embedding encode the position to each token in a sequence. So BERT knows the order of the words. Then the final input representation of each token is the sum of the token, the segments, and position embeddings. So after processing these embeddings through multiple layers, BERT produces contextual representations for each token. Next slide. So in my code, I use BERT as a feature extractor to capture semantic relevance between the query and the documents. So I use pre-trained BERT-based encased model to do. And for each query and each document, I generate the fixed length embedding using the representation of the CLS token. Then I compute interaction features between the query embedding and the document embedding, including like cosine similarity, L2 distance, and dot products.
No problem.
So these interactions features summarize how semantically similar the query and documents are. Next slides. So in addition to BERT-based semantic features, I also extract simple lexical features. So while BERT captures semantic meanings, lexical features focus on surface level matching between the query and the documents. So I include features such as query length, documentary length, token overlap counts, overlap ratio, and Checkaard similarities. So these features capture exact words matching the signals that semantic embeddings may smooth out.
Very good.
Next. So I output the extract features into NumPy files that are directly used by the modeling stage. So for each dataset split, I provide a fixed length feature matrix, which each row corresponds to one query document pair. So the row order is preserved exactly so the features are aligned with the original pair files. So these feature files can be directly loaded and used by ranking models such as random forest and LambdaMART. And I also provide a feature name file to document the meanings and order of each feature dimensions. Next slides.
He's not here, so we gotta skip this part.
I mean, if you want to go through it, do you if you want to go through these slides, just yeah.
Nah, I didn't
Okay.
read his slide.
All right, learning to rank. Next slide. First of all, what is it? Learning to rank is the problem where if I have a query queue and a list of websites called documents, then I want an output that ranks this list of websites in the most important. Next slide. So that would be like a Google search, or in our example, it is like a Stack Overflow question. Okay, next slide. Now we want to solve this question by training a model that can look at a question, an answer to a question, to the query, and then it can assign it a score, a relevant score, such that after it has assigned a score to all the answers, the list can then be sorted. Now there are several ways you can do this. First of all, there's a crude way where you do it pointwise, where you just do it point by point. Problem being here is that when you do it as a point, you lose the relevancy we are comparing an entire list and not just point by point. So if you do it pointwise, you will sort after you're done with finding your relevance, and therefore the actual entire list is not taken into account. This is improved if you do it with pairwise, which is what most models, or at least the models that we work with, do, where they compare two questions to each other and say which one is the best. Would I improve my score ranking if I put one xi over xj? Doing this list-wise, it's not really something we do, but instead we just iterate multiple times on our model such that they are all compared to each other. Okay, next slide. Okay, so this is the models that we use are this LambdaRank and LambdaMART, where LambdaRank is just providing this gradient based these gradients, lambdas, to determine whether or not we improve our model by taking xi over xj. So you can see in the mathematical model here, there is some difference, sigma si minus sj, and then it's compared to the NDCG, the normal discrete cumulative gain or whatever I think it's called. I can't remember the abbreviation. And LambdaMART is basically doing this, but where you create a forest of models instead that will create an ensemble so that we can have and where it then becomes a voting system. Okay, next slide. So we do this. We use a Python library called LightGPM, where we do it first for one, but since it's a one time, but since it's a forest, there are several factors that we can optimize for, such as learning rates, the number of leaves, and the depths of our trees. Doing that, we then get not only that in our model that the how long an answer is by far the most important feature in this gain, Yeah, I think that is basically what I had to say.
I see. So in this first analysis, the length of the query is the most significant.
Yeah. As long as I've understood the features correctly. All the others are comparable, but the length
is the one the most discriminating.
Yeah, and I mean personally, when I go into a Stack Overflow, the longest answers are usually the ones you go for because they will actually explain. I know it's not Stack Overflow.
Exactly. That was before
Yahoo.
ChatGPT.
Yeah.
Very good. Okay. Yeah. So I understand.
Okay.
Can you just go through the slides that you guys skipped? Just show me a little bit the slides that you didn't present, just for me to get an idea. I think they were just 3 or 4 slides, right? Can you show me those slides? This is the BERT, right? So that was okay. That's the difference between train and test. The long tail. Yeah. Go ahead. Feature embedding, that was good. That's nice and easy. BERT was pre-trained, 724. Around 4 baseline. Yeah, this one here. Yeah. Go up a second. Feature. Just show me. Go up a second. Go to what 9. Let's say 18. Slide 18 to 20. Show me a second. Okay. Stay here. Okay. And then let me see. Yeah. Okay. Cut. Understood. Yeah. So the same message basically. Understood. Okay. Yeah, because yeah, no other comments. Yeah. I understand. So how many? What was this? The 5 after you did the data cleaning. What's the size of the training and the test set? Do you remember, guys? Do you remember what's the trainer? What's the size of the data set after you do the cleaning?
It's not very large,
Yeah,
at least. Yeah.
I think.
The models at least run very fast.
Yeah.
Even when doing different combinations, it was 1.7 seconds. So not much data, I think.
Yeah. Because then there was the part. There was also the part with the context, right? You guys didn't do that part, right?
Maybe.
I don't think we've done the part with the spice.
Got it.
Like here's the count of the queries, and the query size is not very large. You can see, if there's 15 answers, then the query size is 15. So the query size is pretty small, and there's not many queries.
Yeah.
And this is the clean one, so it's even smaller.
Okay, very good.
Yeah.
So I hope you had fun doing some NLP. Tell me about the final project. You guys are already working on the final project. Do you have any progress? Do you have anything to report regarding the final project?
Not really. Yeah, we're gonna discuss the final project these 2 days.
So next Wednesday, right?
Yeah, let me check the date because I'm terrible with dates, guys, right?
It's next Wednesday.
Okay, good. Hopefully you'll manage to.
Well,
January
don't
14th.
we?
Yes, we have 1 week.
Yeah, don't we all have break now? So
yeah, exactly.
We have more time.
That's a good thing. Yeah. Okay, very good, guys. And I'm looking forward to the final presentation from you guys. And hopefully next time we can all be online at the same time.
Yeah. And if you got any problems of the the node things or the FPGA things, the AGI. You can ask me anytime. Yeah.
Very good, very good, very good. Very nice to learn from students, you know. Okay, thank you so much, guys.